Welcome to a new episode on the Technomora channel. We really hope you will enjoy watching it and invite you to tell us what you think of it by leaving your reactions below the video. And now, please allow me to present your host, Technomora.
Hello, my dear viewers. Today we are going to build a clock, date, temperature indicator or panel, if you wish, based on a few components and built around a small processor or controller which is called a Digispark. I already introduced to you the most obvious part of the design, which is the display. And the display consists of 8 LED panels, let's say, or indicators, which are driven by a chip called MUX 7219. You can buy these little displays for, I think, even under $1 on the internet. In fact, I bought this one on eBay. But to drive the display, we also need another component, which is that little thing over there, and that is a timer breakout board built around an IC which is called a DS1302. Alright, moving on, we also have this part, and in fact this is, let's say, the heart of the design. This is a Digispark, or more precisely a processor called an ATTIny85, and it's built on a tiny board of its own, and it has also a built-in USB connector, as you can tell. And that is essential. If you're going to build today's design yourself, I would advise you to buy a Digispark with a USB connector like mine. That will make your life a lot easier. And then finally, on that little breadboard you see here, you see a temperature sensor which I built around a few components, and the main component really is an NTC, which is the shorthand for negative temperature coefficient resistor, and it's that little black thing you see right here. Alright, so the whole sensor is built around that part there. So basically the whole design is built around 3 chips and a particular component which is called an NTC. And obviously the 3 components I'm talking about are an ATTIny85, a DS1302 Timer chip, and a MUX 7219 display driver. And this one is particularly made to drive 8 LED display blocks, like you see over there. And these components, these 3 components, are obviously all digital. Now, as you all know, if you want digital components to talk, quote unquote, to each other, you do need a certain number of, I would say, connections. And the most important connections between those components are threefold. And the connections that you will need is a clock, an input-output pin or a data pin, and a chip enable or a chip select pin. Now, all these ports on digital chips generally have the same designations. Okay, so I said, for example, chip enable, but on some chips it's also called chip select. Alright, so yeah, you have to get used to the fact that these different signals you see here, signal pins, are designated by all sorts of shorthands like these. Yeah, but in the main you'll see these ones here. So CLK, SCLK for clock, or CS for chip select, or CE for chip enable. On certain chips you might even find a pin called load. Okay. Data pins are often written as DI or DO for data in and data out, or even DO, so data in out, or even in out. Yeah. On one of the chips, the MAX 7219, it's even called SDIN, which means serial data input. So yes, you have to get used to that. It's not unimportant, and you'll see further on why. So here you have a close-up of each experimental board you can buy on the internet. Alright, and like I said, if you're a little bit savvy and you look around, you can buy these components, I mean all together, maybe like for $5 or so, maybe even less if you're lucky. But yeah, these particular boards are really inexpensive. Alright, so you don't need to spend a ton of money to acquire them. Notice the labeling of the pins. Alright, so on this particular Spark I bought, the Digispark, on the upper side of the PCB the pins are labeled from P0 on the left to P5 on the right. Alright, but on the back side they have labeling which is a bit more explanatory. Alright, and if you look up information on the Digispark, these abbreviations might be slightly more informative for you. To power the processor board and all the other boards, by the way, I'm going to use 5 volts. Alright, and the 5 volt is connected to the lower left pin. You see there, 5V. Alright, so that's where you connect the 5 volts, and then the G and D obviously is the ground pin. Alright, so those are the pins that I'm going to use for connecting all the boards up to the power supply. And the plus 5 is connected to VCC, and obviously the ground is to G and D. You see those 2 pins there. And then for the clock, it's the same thing, VCC and G and D. Now notice that the order of the let's say control pins, so the clock, the data, and in this case RST, but which is really chip enable, okay, are not the same order on both boards. Alright, so data is the center pin here, data in is the upper of the 3 pins, right? So yeah, you have to keep that in mind. So the order of these pins is not necessarily the same everywhere, and where in some chips the chip select is designated as CS, right? In others, apparently, it's designated as RST, or possibly reset, but which, if you read the specifications of the DS1302, is really a chip select pin. Alright. Now, you don't see clock, data, or chip select pins on this little board here, because this is the Digispark. Alright, so all the pin connections you see are either for power or are selectable via software. You know, programs you will write or install on the Digispark. Now, the most interesting part of this specific little board is that it has a USB connector. Alright, and you will have to use this to program the processor or controller, which is that little black square chip at the top. Alright, and one of the advantages of using the USB connector for programming it is that you don't need a separate power supply. Yeah, it draws its power from the USB connector. And if you're a bit clever, by connecting the 5-volt pin of the Digispark to any of your other boards, you can power these other boards too via your USB connector. Now, mind you, be careful never to draw too much power through the USB connector, alright? There is a limit. I think USB 2 can source something like, but that's a real maximum of 500 milliamps, okay? But this design that we're going to finish now, building, uses at most 50 milliamps, and that should really pose no problem whatsoever for a USB connector. You need a number of pins to have chips talk to each other, alright? And up here in this little diagram here, you get a bird's eye view of what I mean by talking to each other, alright? So remember these 3 pins here: clock, data in out, and chip enable or chip select. You always need these 3, at least these 3 pins, to talk from one chip to another, alright? So up here on the diagram, you see a little block here which is called the CPU controller, alright? And then next to it you see the symbolic representation of a timer controller, which in our case is a DS1302. And then here you see a block which represents the display, which is built around a MAX 7219. Alright, now to control what's on the display, the processor needs to send data to the display, obviously. The display can't tell or can't know what it needs to display if it doesn't get the data in the form of bytes, which are sent from the controller to it. Now, the display can't tell without the clock and enable pin, whether it is to display data and what data to display. In other words, the processor needs to tell to the MUX7219, hey, I want to write some data to you to display, so please be ready. So what it does is in this case, it pulls the pin chip select low, so it sends a low to the MUX7219 to tell it be ready to receive data. Then it sends clock impulses, so very precise impulses, one after another, to the MUX7219. And at each clock impulse, it sends a bit to the chip here. So the chip knows when the chip and the chip select is pulled low, okay, whatever bit comes next on the data line, that is data that I need to display. And it counts the number of bits and it reads the bits which are offered to it with every clock pulse. Alright? So every clock pulse it reads a bit and another bit and another bit. And when it counts 8 bits, it knows it has received 1 byte of data. And that is what it does, one after another. Now, the data, quote unquote, can literally be something to display or can be a command to do something else. In this case, it could be, for example, to diminish the brightness of the display, for example. Alright? Either way, the MUX7219 will only start working, actually working, when the chip select is pulled low and when it receives clock pulses. And once it does that, and you offer it a signal in the form of either 0 or +5 volts on its data pin, depending on the first few bytes it receives, it knows what to do. On its own, the Spark, the Digispark, and the MUX7219 can do pretty much everything which needs to be done. Namely, the Digispark can do some calculations or some measurements and then send it out to the display to show to whomever is using this. But in this design, specifically, I wanted the processor to display the time and date of day, alright? And on the market you can get a little timer chip which is called a DS1302, alright? Now the DS1302 is specifically built to keep the time very accurately, alright? So there's in the chip is a little timer built in which is controlled via a tiny little crystal, and it keeps precisely track of the date and time, and you can even set the date and time on the chip via the processor, so that even when the whole apparatus is switched off, thanks to a little backup battery on which is connected to the controller, the timer controller, the timer will keep running for as long as the backup battery runs, and that could easily be a couple of years or even longer. depending on the state of the battery. So again, when you want to either write or read to this chip, say you want to set the date and time, the processor has to send a chip enable signal to the timer. Alright? In this case, the chip enable is a high. In other words, the ATTINY85 sends a signal of plus 5 volt to the DS1302 CE pin. After doing that, it starts sending clock pulses, and again, just like with the display, every pulse it sends a bit into the data pin of the timer chip. And the timer chip knows, thanks to the first few bytes it receives, what it needs to do. So generally the first few bytes are commands like, for example, please accept the next few bytes to set date and time internally. That's one example. Another command byte, so 8-bit, could be please send back the date and time to me. So in this case, the ATTINY85. Remember, the clock pulses are essential. They time precisely, and they enable both chips to time precisely when to either send or receive a bit of data. Alright, now one of the nice things of the Digispark is that it also has an AD pin. In fact, it has 3 AD pins, but we're only going to use one. And what I mean by AD, which is an acronym for analog digital converter. Alright? In essence, within the chip, there is a device which reads a certain voltage on one of its pins and then converts it to a decimal value, like a value between 0 and 1023. So what you need to do is in effect create a small voltage which you then send to that AD pin. In this case, we'll use pin 3 or PB3 of the Digispark. And the Digispark will convert that voltage we send to that pin into a number, say 539, 762, even 1011, for example, or 0 for that matter. So the AD pin, so the analog digital converter pin, will read the voltage which is applied to it and convert it to a number. The processor will do some calculations based on the number it receives, and then will transform it to a temperature. And that temperature will be sent as a series of bits and bytes to the display. So basically, if you're going to build a clock, date, temperature display, you will need only a little bit of work and make a whole bunch of connections with little wires or little pins, but I can safely say this is, well, basically an hour or an hour and a half of work at most, and then, yeah, there you go. You can make it work. Now, calibrating it will take a little bit more work, and you will need to calibrate it with two potentiometers. You see there, I use multi-turn potentiometers, and you will have to calibrate the sensor, obviously, in such a way that obviously the temperature which the program on the processor receives can interpret as a temperature. Alright, so the voltage must be correct, or the processor will struggle to transform the temperature. Alright, so right now the display shows 19 degrees, and I have another thermometer here just to have a reference, you see. So the temperature in here right now is 19.7 degrees Celsius, and that is what the display on my design is showing. Obviously I don't show the decimals, but if you're handy enough, you could program that too if you really wish to. Alright, so how do you calibrate the sensor? Well, I think the easiest way to do it is to disconnect it from the processor and then connect the sensor separately to a power source, like a variable power supply or even a battery or whatever, anything which gives you plus 5 volts. And then by connecting a multimeter and measuring DC voltage, alright, by measuring DC voltage between ground and the output of the sensor, which is this pin in essence, but I also connected a long yellow wire there to the same pin of the sensor. By connecting the multimeter to the output of your sensor, you will get a voltage, and right now the temperature is 19.7 degrees Celsius, so you must have a voltage of around about 2.3 volts, 2.2 volts, and that should do it. Now remember, this voltage is highly dependent on the type of NTC you will use and the quality of the components and everything like that. Now, if you watch the display of the digital multimeter, you will see that it's a little bit jittery. Okay, so it jumps around a bit, roughly speaking 40-50 millivolts. And that is the result of the fact that, it's built on a little breadboard with a lot of wiring, loose wiring everywhere. Okay, very long and loose wires. And unfortunately, these long wires pick up all sorts of stray signals. And that make those stray signals, are being picked up by the sensor and are translated by, let's say, a very jittery output voltage. But since the Digispark only measures for a certain length of time and only once every 6 seconds or so, the display is relatively stable. Alright, so one word of caution though, this is not an extremely and you can, oh well, it's already gone, but this is not a super reliable temperature sensor. Okay, so if you're going to use this, say, to regulate a heating or whatever, or anything else, yeah, you do so at your own risk. It's basically for display purposes, it's okay. But if you're going to use this for medical applications or chemical applications or whatever needs precise temperature measurements, then this is not the thing to use. Alright, as I told you, to be able to direct, so to speak, the timer or clock chip and a display chip, you need 3 lines. And you see both chips have a data pin, a clock pin, and a chip select pin. Alright? So the Digispark, which is represented by this symbol here, doesn't have a clock or data or chip select pin as such, but it has 6 multi-purpose pins which can be programmed to do whatever we want them to do. And in this case, we will program the pin PB0 to be the data pin, which either sends or receives data between the clock and the display. Then we have the pin PB1, which will function as the clock pin between the clock and the display. And then we'll use PB2 and PB4 respectively as chip select pins. One pin will select the clock, the other pin will select the display. Now, the ATTiny has 6 pins, general purpose pins, which are numbered PB0 to PB5. I could have used any of those, well, technically any of those pins to do whatever I want the processor to do, but I used those pins in that particular order. If you want to use different pins, that is up to you. You only need to program them, and I'm sure you could make it work with a little bit of programming. There are 2 pins that are a bit special. Namely, I use the pin PB3 as a analog digital converting pin. Alright, so the task of PB03 will be to read a certain voltage which it gets from the temperature sensor and to convert it to a particular value which corresponds to a certain temperature. Alright, PB5 is in essence a reset pin. In other words, if you connect that pin to ground, it resets the processor and therefore, of course, all the peripherals too. So we won't use pin 5, but technically you could use it to do a hard reset of the whole device. Now, to program a Digispark ATTiny85, you will need a program which is basically free and which you can download from the internet, and it's called an Arduino sketch editor. Alright, I'll put a link below the video where you can download the sketch editor. Now, unfortunately, maybe you will also need to download and install an ATTINY85 driver for the sketch editor. I'll also put the link below the video where you can download the driver for the Digispark and the installation program in effect. A few things you should remember is that basically the sketch editor is a C++ editor compiler, and which has some very specific Arduino functions built in. So you could say the C++ they use is enhanced with a few typical Arduino instruction sets. Alright? Now, what you're seeing here is part of the program that I wrote to drive the display with the Digispark you see over there. Alright? So this little thing here has been loaded with a program which you see there, which is in Arduino speak called a sketch. I don't like too much that term, but basically it's just a program, okay? And the program is written in human understandable language, so C++ and a few Arduino instructions, and this program will translate these instructions to understandable instructions for the processor. Alright? So the Digispark obviously doesn't contain an interpreter, but is a very, very simple processor which needs commands in byte form. Yeah? So in fact, you could say in machine language. Alright? So this program allows you to write a program, to compile it or to transform it to bytes which the processor, so the ATTINY85, could understand and execute. It also has an option to send a program to the Digispark. Alright, so if you look here, you see the sketch menu option right here. And there you see verify, compile, and upload. And basically these two instructions are what you're going to need to upload whatever program you write to the Digispark. And I'll make you notice that the Digispark is connected to in this case my laptop via a USB cable. Alright? And it's connected to the USB port of my laptop. Alright, so basically there's a lot of instructions in here, but basically what the program has, and I'll show you quickly what the main parts of the program are. After the program initializes a few things, alright, a few variables and all that, it comes into a loop, and that large big loop does nothing more than reading a time and a date from the clock chip or the timer chip and send it to the display, or read a voltage from the temperature sensor, translate it, and then send that to the display. Alright, so that's, you could say, the main part of the program. Now, I wrote some specific functions to to do some basic operations between the processor, so the ATTINY85 or the Digispark, and the display and timer chip. Alright? And I wrote those functions because, it makes programming the Digispark a lot easier. Yeah, so I wrote some function which is called blank display, which, well, the name of the function says it all. It blanks the display. Alright, so it clears whatever is on the display. Then I wrote a function which is called sendWord, which sends data to whatever device is hung to whatever pin. Yeah, but remember the pins that I explained to you. Alright, so here you see that it sets the pin 0 for output. Alright, and here you see it sets the pin 4 for output, and which will be used for chip select. Alright, and then you see that I can write to whichever pin I designate either a high signal or a low signal. Alright, which in our case would be either 0 volts for a low or 5 volts for a high. Alright, so in effect here, for example, you see how I send data to either chip, so the timer chip or the display chip. Don't worry, any subscribers of mine can get the program for free. So if you subscribe to my channel, sending me a simple email, I will provide you with the program. Alright? So, except for sending data to one of the chips, I also wrote a function to receive data. Alright? In this case I call it receive word, the function. Alright? And then I made a specific function to set the clock. And then I made a specific function to read the sensor, the temperature sensor. Alright, so there you go. Oh, and by the way, you can display temperatures either in Celsius or Fahrenheit. In my case it's Celsius, since, in Europe we use Celsius. Alright, and then there are some ancillary functions which basically I don't use yet, but which I programmed for test purposes. I'll leave them in the code just in case you would want to do a few tests of your own. Alright? So I'm not going to go too deeply into the code that I wrote. Like I said, if you are subscribed to my channel, sending me a simple email, I will respond by sending you back the code. The only thing you need to add in the comment or the subject of your email is sketch Digispark temperature, date, time indicator, and that's enough. Okay, I just need those few words in the subject just to know that it's not spam being sent to me. it pays off to try out or to make a mock-up of what you're going to build beforehand, alright? Just to try out the positioning of the different components that you're going to use in your design. And in this case, I decided on using a print board like this, alright, which is like a perf board, which you can use for experimentation, alright. And I decided to use a perf board as a support for all the other boards, and I'm using little plastic standoffs, alright, so to create enough space between the boards. And I made use of the holes that are drilled into the boards to attach them to each other with little plastic standoffs. I have a whole collection of standoffs. So, and I picked and chose the right sizes of standoffs to create just enough spacing between the boards, but not too much, so as to make it too big. And then the two front standoffs you see on either side of the display, I'm going to use to attach the whole device to the front panel of something else I'm going to build, and of which you're going to see a video soon on my channel. Alright, I'm going to just add a few more things, because I think the video is already long enough, but I'll give you a few tips. Alright, so you see here that I said things to remember. Now, I told you that you need to use an Arduino sketch editor with a Digispark 16.5 megahertz driver. Okay, this is essential if you're going to use a Digispark to the fullest of its capabilities. Also, I told you to get a Digispark with a mini USB connector and a bootloader already built into the chip. Yeah, bootloader essentially is just a little program which it has in memory, which enables to load your program, which you programmed, automatically, and start your program automatically. Okay, so but if you buy a Digispark, with a USB port, generally there is already a bootloader installed. Obviously, you need a laptop or a PC with at least one USB port, and preferably Windows 10, although I used it on Windows 7 too. So Windows 7, I think, would work as well. Also, I told you that basically the language you use to program the Digispark is C++, but C++ enhanced with a few Arduino functions. Alright? Now, there is something you really need to know. If you're going to use my program, which I wrote for this design, then you need to do a few things in a specific order. First, you will need to remove the battery, the backup battery of the timer, alright? And you will need to physically disconnect the output of the temperature sensor to the Digispark. Alright? That's the first thing you need to do. Then you need to compile and upload the program via a USB cable all the way into the Digispark. Alright? Once that is done, then you need to disable the small code in the program, which is this code here. Now let me show you. So in the setup of the timer, which is this part of the code here, you see it's all commented out. So if you take away the comments and you send the program towards the chip with the appropriate values you see here, which incidentally are literal values. So you see here the seconds, 0 seconds, 22 minutes, 13 hours, or the 4th day, the 13th day of the 11th month of the year 20. Alright? And this code indicates the day of the week. So 4 in this case is a Wednesday. So if you uncomment these lines and you send this to the Digispark, you will program the clock or set the clock or timer chip, the DS1302, to the exact time and date you desire. Alright? When you uploaded the program with the time and date you wish to have, you need to comment out again the lines and send the program to the Digispark again. Alright? This is essential because if you don't do it in that order, you will reset the timer again and again and again. But you only need to set it once and only once by uncommenting these lines once and sending them to the Digispark once. Alright, so once you've done that, what you need to do next is you put in the backup battery for the timer. Alright, so this is a cell battery, and if I'm not mistaken is let's see, what is it, a 2032? A 2025. Alright, so you need a 2025 battery backup cell. Alright, once you've put in the battery into the timer, you can safely switch off the whole apparatus. It will remember the time and date no matter what. Yeah? Thanks to the backup battery, it will remember the exact date and time. Now, remember, I told you that you need to disconnect the, at least if you're going to use my program, you need to disconnect the temperature sensor pin before you load the program. Alright? And the reason for that is that pin 3, so PB3, is actually used for a USB connection on the Digispark. Alright? If you leave in the pin for the sensor while trying to upload the program to the Digispark, it won't work. So anyway, once you uploaded the definitive version of the program to the Digispark, so without the timer setting section which you commented out, you can reconnect the you can reconnect the sensor, the temperature sensor pin, to the Digispark, and then you're done. Alright, so I connected up all the print boards of my design to each other. Alright, and right now I'm monitoring the output of the sensor so that I can calibrate it to show the temperature inside of the room I am in. And right now my reference thermometer says it's 18.8 degrees C. Now remember, this is only a household thermometer, not very accurate, okay? So, but give or take 1 degree C, I'm reasonably close to what the calibration should be. It's actually still a little bit low. As you can tell, it's displaying the temperature inside the room as 17 and not 18 degrees. So I managed to calibrate the temperature by setting the 2 potentiometers of the sensor. Yeah. And obviously I hooked up the whole thing to my variable power supply, which is supplying 5 volts DC at, let's say, roughly 35 milliamps. Right, so by tweaking the value of the 2 potentiometers of the sensor, you can set the output voltage of the sensor, which ultimately is interpreted by the Digispark and calculated as a certain temperature. Now, 2 tips. If you're going to tweak the output voltage of the sensor, start by mechanically setting both potentiometers somewhere in the middle, and from there you tweak the output voltage of the sensor until you get a temperature close to what your reference thermometer tells you it is. It's that simple. Also, I would give you the advice of letting it heat up for, say, 5 or 10 minutes or so to make sure the sensor is to the right temperature inside the room. Lastly, I would give you as advice to build the whole device into a metal case, okay? Not a plastic one, but a metal one. Because if you're going to monitor the output voltage of the sensor, you'll see it jump around by a few millivolts, you know, say 30, 40 millivolts. And the reason for that is that all the wires of your design pick up stray signals from all around you, from other appliances and such. So you have to shield those cables properly in order to avoid sudden jumps in output value of your sensor. The ultimate test, of course, to see whether you calibrated the thermometer or sensor correctly, is to see whether if you touch the NTC, which is the actual sensor, whether it will display your body temperature or not. So which should be in degrees Celsius at least, somewhere between 36 and 37 degrees C. So let's have a go. It should take about a minute or so to display the temperature. 35, 36, There you go, 36. So my body temperature is probably, well, 38, yeah. It varies a little bit, but remember, when touching the sensor, I also induce some noise into the sensor, which it picks up. But there you go. The temperature stabilizes around 37 degrees. Yeah, 36, 37. So I would say my thermometer is calibrated correctly, which is great. So now the temperature should drop back, and it does. Great. So I think this was calibrated correctly. There you go. So there you go. A final look on a homemade clock date thermometer. Remember though, this is not intended for use in either medical or chemical applications, alright? It's not accurate enough as it is built here. But for simple household use, it's more than good enough. Alright? I still need to tweak a little its calibration, but I'm getting there. It's a simple matter of finding the right voltage, calibration voltage. Alright, well, I hope you enjoyed watching this video on how to build your own clock, date, calendar, thermometer around a Digispark ATTINY85. Remember, anyone who subscribes to my channel and sends me a simple email mentioning the title of this video in the subject can request a copy of the C++ program I wrote for the Digispark. So there you go. I hope you enjoyed it. Thanks very much for watching, and I wish you a lot of pleasure building your own little design, and I hope to see you soon for my next video.